Hey then, and welcome to this next lesson on high-level mathematics, algebra. So we're continuing now. We're going to be taking things a step up now to non-linear equations. So we focus mostly on linear ones, which are more straightforward. Non-linear equations can be a little bit more tricky, but we're going to see what the different types are and how we deal with each. So first of all, we need to take a look at some indices and surds. Like we've looked at that when it comes to numbers, but we're looking at it now in the context of algebra. We're going to look at how to deal with brackets. Important thing, if we're trying to evaluate an expression, brackets is the first in our, BIDMAS order of operations, isn't it? Then we look at quadratic equations. Now, this is the most important non-linear equation that you're going to work with at GCSE level. So we're going to be studying these in depth and what their properties are. We'll take a look at algebraic fractions, um, which is another type of non-linear equation. Uh, Quite an important type, can be a little bit tricky. We'll see how they work. And then we're going to look at just general other non-linear equations that you can encounter, which are less common, and they can have their own quirks, their own sort of tricky aspects that we have to know how to deal with. So we'll see what those are. But first of all, indices and surds. So we've got lots to get through today. Um, right, indices and surds. So we've seen before how we can combine powers with numbers. Say if you had 2 to the power 2 times 2 to the 3, we see the powers add, you essentially get 2 to the 5. Well, we can extend that idea to algebra. It's going to work in the same way here for an unknown number a. It's still just a number, and so the same rules will apply. Here, as long as the base is the same, remember that's important. So a to the power 4 times a to the power 3. If it was like a and b, for example, then it wouldn't work. So here, we've got the same base again, and you see the powers subtract because it's division. Here, when we have n to the power to another power, those two powers multiply. Here we have when we're doing a negative power. What does a negative power mean? It essentially means to take the reciprocal. So we do 1 over that number. Or if it's a fraction that we're taking to a negative power, then the fraction is just going to flip upside down. A fractional power is basically saying do the opposite of a power. So rather than doing to the power 3, we're doing to the power 1 over 3. That means do the third root. So it'd be the cube root of r. So you see that it works in very much the same way. If you're not so familiar with indice laws, go back to that earlier lesson on numbers when we was looking at indice laws. So these are our, key laws really that we need to know. And if you can know and really understand these, then there's a lot of problems we can solve, more complicated ones. So say if we took one like this, p to the 4/3, well, you can see we could split that up like that using, the third rule that we have there. So it's going to essentially be like this. It's like a power to another power. And so we can see that's basically p to the 4, and then we're taking a cube root. So we don't really have to do all those steps every time. I'm just sort of showing it more explicitly. When you do say p to the power 4/3, the numerator of that power is just a power in the usual sense. The denominator is then the opposite of the power, so it becomes the root. We can have something like this. We've got a little bracket there, so we're doing 4x squared cubed. So x squared cubed, we know the powers multiplied to get x to the 6. But the important thing there is because of the brackets, the 4 is also getting cubed. So we need to be aware of that. The 4 is getting cubed as well. And so it becomes 64x to the power 6. You could take something like this. We've got 5 to the power, 5 divided by m to the power minus 3 over 2. So there's a lot going on there. How would we simplify that? Well, we'll break it down. Like, first of all, okay, that m to the power minus 3 over 2 is basically 1 over m to the 3 over 2. Now, so we're dividing by a fraction. We saw in our proportions lesson that we can do that, can't we? Dividing by a fraction is essentially the same thing as timesing by the reciprocal of that fraction. So it's basically timesing by, no, 5 times by m to the 3 over 2 over 1 instead, which over 1 is basically doesn't change anything, does it? So it just becomes m, 5m to the 3 over 2. So you see there, from those few basic laws, we can then simplify a lot of other more complex indices and surds problems. So we need to be mindful of those. And yeah, that m to the 3 over 2, yeah, you see, we could split that up into a root and a power if we wanted to, but that might not be necessary here. So, okay, so here's our key laws that we need to be aware of. So let's keep those up there for referring to. We might have situations like this with numbers again that we have to simplify. The key with this is we need to basically we need to get the base the same. So here we've got one base of 5 and the other base. So it's basically a base to a power. That's what those words mean. So we've got a base of 5 on the denominator. We've got a base of 25 on the top. Okay, if we put it like this, we can make the bases the same. So 5, put 25 as 5 squared. So on the top, we basically have 5 squared cubed, which comes to 5 to the 6th. Now that the bases are the same, we can do that division, can't we? It's going to be basically 5 to the power of 6 minus 8, which is 5 to the power minus 2, which we know is basically 1 over 5 squared, because the negative power means to take the reciprocal. And so we can simplify that to be basically 1 over 25 if we wanted. So there you go. You see through our indice laws, we can take something that looks quite complicated and it just becomes the fraction 1 over 25. You could take something like this. Remember that our roots and powers, if it's being done to some two things that are being multiplied, we can distribute that over each of them individually. So you see, if we first simplify what's inside the bracket. So we had 27 to the power 4 over 3. Well, we know that denominator 3 means to take the cube root. So we do the cube root of 27 first. So, okay, so we've got 3 to the power 4 there. 2 to the power 10 stays the same. Now we could distribute that root over the two things inside that are multiplying, which we know a root is basically the same thing as a power half. So if we're taking each of these things to a power half, we're basically timesing each of the powers by a half. So 4 becomes 2, 10 becomes 5. And in that, we could then just calculate, couldn't we? Quite easily. So if we was doing this on paper and we didn't have a calculator to work this out, that's one way we could simplify it to a point where we could work it out. Now you could take something like this, where there's a lot more going on. With something like this, what we want to do is typically we want to bring together our terms first. So you see on the numerator, we've got two things multiplying each other. We bring together the common numbers, the common parts of each of those terms. So you've got 15 times 3 gets 45. The x squared times x to the 4 will be x to the 6. Y to the power 5 times y to the minus 3 will be y to the power 2, just using our indice laws as usual. Now we've got just one term divided by another term. We can then continue to use those indice laws. Like we can split it up into the number parts, the x parts, the y parts. Those are the parts that are going to cancel out on the top and bottom of the fraction. So we've got 45 over 18 can simplify to 5 over 2. X to the power 6 over x to the minus 1. So that's going to be x to the power 6 minus 1, which becomes x to the 7. Y squared over y to the 1, essentially, is going to be y to the power 2 minus 1, which is y to the power 1, which is just y. So you see how that can simplify down to essentially 5 over 2, x to the 7, y. So even quite complicated looking situations like that, if you bring things together as much as you can, you start to cancel out the common factors of numbers, x's and y's, and you can simplify it down quite significantly. So one application of that is say what we've already seen before with highest common factors and lowest common multiples. A quick example here. Say if we had something like this, where we've got these two numbers and they're partially factorized into these prime numbers, but they're unknown prime numbers. And we want to find out what is the highest common factor and lowest common multiple in terms of these unknowns. We can do that. Like, okay, if we continue to factorize this into its primes, because 12 and 8 are not prime numbers, are they? So we can split it up like this. So yeah, examiners love to ask these kind of questions because it's taken something that you might already be very familiar with, like highest common factor and lowest common multiples, now to do that. And now you need to apply it in a more novel way. So we know how to do it in theory. Like we need to break the two numbers down into their prime factorizations, which is what we've got. Now, highest common factor, you basically want to choose the highest number of factors you can from both numbers, as long as it's common to both numbers. So if we look here, factors of 2, A, B, and C, we've got common factors, haven't we? 2 squared, we can take 3 factors of C, only 1 of A and B that they both have in common. And so this would be their highest common factor as an algebraic expression. And we can simplify that to this by doing the 2 squared. Similarly, with lowest common multiple, we want to take the highest power of each prime factor. And this will then produce a number that is a multiple of both of the numbers, because both of these numbers are then contained in it, but we haven't included any unnecessary factors, and so it's the smallest possible multiple that we could get. And so, yeah, once we've done that, we could then do the 2 cubed times 3 if we wanted to. So if that's confusing, you might want to do a little recap of what highest common factor and lowest common multiple is, like precisely what those steps are, how we calculate each, and then come back to this, and you see how we're applying it here in the same way with prime factors. It's just we're dealing with unknown prime factors. We've got, so they're labeled by A, B, C, D, but it's the exact same steps. And yeah, we need to be able to do that. One last thing we need to be aware of is something known as rationalizing the denominator. So if you have something like this is something typically we want to do as mathematicians, because it tends to make things easier. It makes things easier to compare if we have a common standard of keeping the denominators rational. Like, because you remember, root 2 is not a rational number here. The square root of any number that doesn't come out to an integer is essentially going to be irrational. So how we could rationalize that is by doing the same trick we normally do with, like, simplifying a fraction, say, where we do the same thing to the top and bottom, like scale it up or down. In this case, what we're doing is we're timesing both sides by the top and bottom by root 2. And the reason we do that is because on that bottom, it's then going to rationalize it, isn't it? Because we'll get root 2 times root 2 squared. The root and the square are going to cancel out. And so you just left with 2, which is now a rational number. And on the top, you're going to get 5 root 2. So the top has now become irrational. But that's fine because we're trying to rationalize the denominator. With something like this, is a bit trickier, but it's a similar technique. What we have to do is you have to times the top and bottom. But this time, what we want to times by is what's known as the conjugate of that irrational number on the bottom, like 2 plus root 2. And what that basically means is you're simply just negating that irrational part, the root 2 in this case. So you need to be able to identify what is the irrational part, which is basically the root. And if we times the top and bottom by that, again, we're timesing the top and bottom by the same number, so it's not changing the fraction at all, like the value of it. So we're going to get something like this, and we're going to have to expand out those brackets. And if you do, you get something like this. And you see what the end result is there, is that denominator has now become rational. It's just the number 2. There's no square roots anymore. But we haven't taken a look yet at how you do something like that. How do you expand these brackets? Like when you've got a bracket times another bracket. But that is the steps for rationalizing the denominator in a case like that, where you've got like 2 terms on the bottom. So now let's take a look at that then. How do we deal with brackets? So first of all, expanding a single bracket is relatively straightforward. You're basically taking what's on the outside of the bracket and you're multiplying it through everything on the inside. So like with the 3x there, when we have a 3 directly next to an x, it implies a multiplication, doesn't it? 3 times x. It's the same thing here. When you have the 5 directly next to the bracket, it implies that 5 is multiplying that bracket. And so it's therefore multiplying everything inside it. So you get 5 times 3x, 5 times minus 4, you get 15x minus 20. Similar thing works for division. Like you can't actually see the brackets there, but it's kind of like 8x minus 4 times by a half. It would essentially be the same thing as dividing by 2. And so it'd be the same thing. We could essentially divide each thing inside just by 2. That's like division can distribute over those terms like that. And the same thing works if we have an unknown on the outside. Exact same thing. So x is still just a number, but it's just an unknown number. So we times it through everything on the inside. So we get 2 times x is 2x, minus 7x times x, minus 7x squared, because you've now got x times x, so it's x squared. You could take then something like this. Bit more complicated. If you've got roots and powers and a reciprocal like we've got there, generally what makes it easier is if we put it all into indices first. So just using the rules like we saw before, we know a root is basically a power half, the reciprocal is a power minus 1. Now if we multiply through, we can just add up the powers. So x times x squared is x cubed, y times y to the half is going to be y to the 1 and a half, so 1 and 3 over 2. You see x times x to the minus 1, it's going to cancel out, and you'll just get 1 times by the y to the power half, which we're also multiplying through by. So we get this. And then we can just convert back to roots if we wanted to. So 3 over 2 is basically root y to the power 3. y to the power half is just root y. So we convert from like our roots and reciprocals into indices, allows us to do our calculations, and then we move back to the way the question was presented is the way to do that. So that's a common thing we do in math. Sometimes we'll change something around because it just makes the calculations easier and then convert back. It's normally easier than trying to do it without doing that conversion. So there's a trick there for when you've got something like that. Expand and double brackets. So okay, that's when you've got something like this where you've got a bracket times another bracket. One way we could see it is essentially kind of like the way we did a moment ago. So it's like we've got this x plus 2 times the x minus 1. Well, what about if we take that x plus 2 and times it through everything in the other bracket? So we've got x times x plus 2 and then minus 1 times x plus 2. Now we have two single brackets, which we can just work out in the same way we did it before. We get x squared plus 2x for the first one, minus x minus 2 for the second one. Then we collect together our like term and we get this. So 2x minus x comes plus x. So the way we usually would do this is more as individual terms. So if we had the same example again, it's like you're taking each term in one equation, one bracket, and you multiply it through every term in the other bracket. So first of all, we'd have x times by the x and times by the minus x to get x squared minus x. Then we'd do the plus 2 times by the x and the minus 1 to get plus 2 minus 2. And again, we collect together the like term of minus x and 2x. And you see we get the same answer, which we should because it's essentially doing the same thing. If you've got two different answers, then something's gone wrong somewhere. So either way around, whatever one works best for you. The one on the right is more common, but if the one on the left makes more sense, that's doable as well. Now let's look at factorizing, which is essentially the opposite. So we have something like this, and we're trying to put it into brackets. So we're just kind of learning general algebraic techniques right now. We'll see how these are actually used in a moment. Now this we could factorize in this way, like this. What we're doing is we're essentially going through one term at a time, and we're trying to see what factors do they all have in common. So 9x minus 15y plus 3, they all have a common factor of 3. And once we factorize that number out, we're going to be left with 3x minus 5y plus 1. So we're basically taking each of those terms and divide it by 3 and then essentially put that 3 on the outside instead. And if you multiply that through using the technique we just saw, multiplying each of the terms by 3, you see it will take us back to what we had at the beginning. We can do the same thing for something more complicated like this. We've just got to go through and look what factors they all have in common. So you look at each part individually. So we look at the number part, then we look at the x's, we look at the y's, we look at the z's. So 4 and 6, we have a common factor of 2. X squared x, there's one common factor of x there. Y cubed y, there's one common factor of y there. And z and z squared, again, there's just one common factor of z. So if we factorize that out, we've got 2x, y, z are all the common factors. And then we put what's left over of each term on the inside. So for the first term, it's going to be 2xy squared. We've taken a factor of 2 from the 4, a factor of x, a factor of y, a factor of z. So all the powers are going to go down by 1. X squared goes to x, y cubed goes to y squared. Z's going to disappear entirely. And then finally, for the second term, you see we've got minus 3z left over if you take out those same factors. And again, the beauty of this is you can always check your answer. If you multiply out these brackets now and collect together your like terms using your indices, like adding together your indices, for your different parts of the term, the number, the x, the y, the z, you'll see it comes back to what we started off with. So if we had something like this, a bit more complicated, what we want to do to simplify something like this, whenever you've got a fraction, normal fraction, algebraic fraction, generally you want to be looking for common factors. So if we factorize the top and bottom in the same way we've just done there, so we see on the top there's a common factor of 5x and y. On the denominator, there's a common factor of 5 and x. We can factorize those out and then cancel them out from the top and bottom because you basically got 5x over 5x there. It's going to cancel out to nothing. Just in the same way how if we had, 2 times 3 on the top and 2 times 7 on the bottom of a fraction, the common factor of 2 would cancel out and you'd just be left with 3 over 7. Same thing, but we're just dealing with unknown numbers. And so it would essentially be this, and that's how we would simplify a little bit. So you see, it's not terribly, simpler, but we've managed to make it a little bit simpler. Factorizing double brackets. Okay, so that's when you've got, say, um, a quadratic, basically, because when we have two brackets like this that are multiplying each other, we can see you're going to get an x squared term, and that makes it a quadratic. So let's see if we multiply this out for the general case. You see, we've got an x plus a and x plus b. So for any general numbers a and b, you see, we're going to get x squared plus bx first. Then we're going to get ax plus a times b. And then if we collect together the like term in the middle, the two x terms, so we've got bx plus ax is going to be, a plus bx. It's basically the same thing we just did a moment ago, but we're just doing it more in the general case for some unknown a and b. And look what happens. You see the a and the b, they add to produce the coefficient of x, and they multiply to produce the constant at the end. And we can use that to factorize. So when we have an actual quadratic like this and we want to factorize, well, first of all, let's look at that number 8 at the end and see what numbers multiply to produce 8. And you see you can get 1 and 8, 2 and 4, or you could have the negative cases because that would also multiply to a positive number. So we've got all the possible combinations that we could have. Now we need to see what combinations will also add to produce 6. And we can see that that's going to be 2 and 4. 2 plus 4 will multiply to get 8, but they'll add to get 6. Therefore, the factorized form would be x plus 2 and x plus 4. And again, we could expand that out if we want to be sure that we've definitely got it right. And so that's the sort of simpler case of quadratics, which I think is relatively straightforward for a lot of people. Where it can get a bit tricky is when you've got something like this. So if we expand this out in the same way we've done before, and we get this and this, and again, you're always going to get two x terms, one x squared term, one constant term. So those two x terms you bring together, you see it's a bit more complicated. So you see x squared now has a coefficient that's not 1. That coefficient of x is looking quite complicated now. But the main thing is that the constant at the end is always just AB. So if we had something like this, it's a bit more complicated. So we can tell it's going to be a bit more complicated because the coefficient of x squared is not 1. So what we do is look at the 16 as usual, and we look at the common factors. And again, there's negative ones as well. You can pretty much kind of list them all out like this. So we know it's got to be one of these two pairs. And, there's not too many combinations. You could almost just kind of guess, a bit of trial and improvement, and you'll find which one is right. But we don't really want to do it that way because that's a bit, it's not consistent. So if you look closely at that coefficient of the x there, we see we get, in our example on the left, you see you basically get 3a plus b. So you essentially get, because there was that 3x there, one of them is going to get multiplied by that 3. And so that's why you get 3a plus b as opposed to just a plus b. So we look here, we look at the 2x squared. We know that's going to get us something like this. We need to do 2x plus something times by x plus something because the 2x times x will get you 2x squared. So we know one of the numbers is going to get multiplied by 2. So we look at our pairs of numbers on the right there and we think, okay, what two numbers will add to get minus 18 if one of them is multiplied by 2? And so that's a little bit trickier to work out. And it takes just a little bit of trial and improvement. With some practice, you'll be able to see it more quickly. But you see it's going to be this one here. And in this case, you've got to be mindful which one is getting multiplied by 2. So in this case, it's going to be minus 2 lots of minus 8. It's going to be 2 lots of the minus 8, sorry. And 1 lot of the minus 2 is what's going to produce minus 18. So because it's 2 lots of the minus 8, we need to make sure that that minus 8 goes in the other bracket to where the 2x is. So that when you expand this out, the 2x will multiply the minus 8. Whereas if it was in the same bracket as the 2x, then it's not going to get multiplied by the 2. So yeah, you could always pause here and try that out. Like say if you swapped them around and you put minus 2 on the right and minus 8 on the left, you'll see it won't work out right. Whereas in this case, it will. So that's how we deal with scenarios like that. You can also get scenarios like this that are less common, but you could come across it where it's a bit ambiguous. So, because here you see we've got 9x squared, that could be 9x times x, or it could be 3x times 3x. Like when you've got 2x, because 2 is a prime, you can only have 2x times x. That's the only combination you can have. But here you could have there's more than one. And so that's what makes it tricky. And unfortunately, the only way we can really deal with that is basically trying one, see if it works. If it doesn't, we have to try the other one. In this case, it would be basically 3x and 3x. And you see, because that coefficient at the end plus 16, it's the same as the one we had before. So we can use our same list of numbers we got there. This time you find the correct pair is this one. Because you see, in this case, because there's a 3x in both brackets, both the numbers are going to get multiplied by 3. So it doesn't actually matter which order we put them in. So you're going to get 3 lots of minus 4 plus 3 lots of minus 4 is going to make up the x coefficient, which we see is, comes to minus 24. So you can see this one is right. So that's how you would deal with this scenario. Like I said, yeah, this is like a very advanced scenario that you're unlikely to come across. But you can see applying the same thinking, you can work it out. And this one can actually simplify to just 3x minus 4 squared because you see it's the same factors, being multiplied. So it's just being squared there. Right, okay, so let's move on because we've still got a little bit left to do. Quadratic equations. So here we've done a lot of the legwork here now. We've learned a lot of the hard sort of techniques that we need. Now we're just applying them to a quadratic equation. So we can solve this through factorization. So say if we had a quadratic like this, and it's equal to something. So we have an actual equation now, not an expression. And if it's not equal to 0, what we want to do is just rearrange the quadratic. So if we've got a whole, we could have an equation on both sides. We've got a mix of, x squared terms, x terms, and constant terms. Doesn't matter. We can move it around, collect together like terms, and ultimately get something like this, where you get an x squared term, you got an x term, you got a constant term equals to 0. And we always want to get it into this form first, certainly if you're going to try and use factorization to solve it. And we'll see in a second why that is. So what we do, let's factorize this now using the skills that we've just developed. So you might want to try that one yourself, but it's I've got the answer here as 2x minus 1 and x plus 1 is what we're going to get here. And the reason why we wanted it equal to 0 is because now we can basically reduce this down to two linear equations, which we know how to solve. And the reason why we can do that is using a important property of 0, which is the fact that if we have two unknown numbers that are multiplying to produce 0, the only way that occurs is if one of the numbers is 0. Now that's unique to 0. It doesn't apply to other numbers, like say the number 12. If we had two numbers multiplying to produce 12, well, it could be 12 and 1, it could be 6 and 2, it could be 3 and 4. It doesn't necessarily mean one of them is equal to 12. But it is the case with 0. And yeah, so think about it for a second. You see that if you've got two numbers multiplying to get 0, one of them must be 0. And so that's why it allows us here, when we've got 2x minus 1 times by x plus 1 produces 0, one of those two must be equal to 0. And so we simplify it into two linear equations like this, which we can solve. And we get two possible solutions. And this is standard for quadratics. You will generally get two solutions. We could try a different one like this. Another, tricky factorization problem because we've got a unit x squared coefficient. If we factorize that in the same way, we get this, which you see we can simplify to this, like we saw a moment ago, because it's basically the same factor times itself. We could now square root both sides to get 5x plus 2 is equal to 0, and we solve that little linear equation there to get x equals minus 2/5. Now, we've only got one solution there, but technically that is still two solutions. It's just the two solutions are the same because we've got two factors there, 5x plus 2 and 5x plus 2. It's just those two factors are the same, and so therefore they have the same solutions. So here, even though it looks like one, it's still technically two solutions. They're just both identical. We can look at a different technique for solving quadratics, which is completing the square, which serves So we're looking at three methods in total. We have factorization, completing the square, and then quadratic formula. Each three of them, they can all be used to solve quadratics, but they have other purposes as well. It's not like we're just learning redundant skills here by doing the same thing in three different ways. But this can be used to solve a quadratic equation. So, and what we do is by completing the square. And the completing the square basically is taking a quadratic and it puts it into this form that you see here in blue. And you might the key property of that is you see before we get two occurrences of the x. We've got the x squared term and we have the x term. And then by completing the square, we're putting it in this form where you see the x only appears once. And that allows us to then kind of unravel this and solve it. So here's like an example. So say if we had x, for this x squared plus 6x plus 1, what we do is we do x plus half the x coefficient, which is 3, and we square that. And if I expand that out, you see what we get. We basically get x squared plus 6x and then plus 9. So we get the same thing as what we got at the start, x squared plus 6x plus 1, but the coefficient at the end is different. So, okay, we've got plus 9 instead of a plus 1. What we can do is subtract the 9 and add the 1. So in general, what you see happens is we subtract the square of that number that's inside the bracket. So plus 3. Okay, we then subtract 3 squared, which is 9. And then we add on the number that we do want, which is plus 1. And so you see this will then be equal to that quadratic. So then finally, yeah, we can do the minus 9 and the plus 1. So you see now we've got it into that completing the square form. And so that's the technique that we need to know. You do x plus half the x coefficient squared, and then if what you do is you then subtract that number inside the bracket squared on the outside, and then add on the number you do want, and you simplify and you see it will come out to if you to expand all this out, you'll see it will come back to what we had at the start. So that's good. So that means it's all equal still. So if we had something like this, it doesn't necessarily have to be equal to 0 this time. We have the same quadratic but equal to 17 instead. By completing the square on it, like we just did, we can now rearrange this. Add 8 to both sides. We could then square root both sides. So we get plus or minus 5 on the right. So now if we subtract 3 from both sides, we've now got minus 3 plus or minus 5, which gets us two solutions, minus 8 or 2. So once we've got it into that completing the square form, we can then solve a quadratic in the exact same way every time. Like the steps are always going to be the same because the square form is always the same. So once you're familiar with that, it'll be very straightforward. And so that's the power of completing the square. But like I said, it has other purposes, which we'll see in a later lesson. So let's look at a more complicated example quickly. So say if you had something like this, and you're asked to solve this by completing the square, what we'd have to do is we need to get either everything to one side or at least all the x terms, like x squared and x term, to one side. Because then we could complete the square on that. But first things first, and this is the key difference here, we need to get rid of that x squared coefficient. So we divide through by 3 to get rid of that. And that's important because that technique we just did won't really work if you've got a coefficient on the x squared. Once we've got rid of that, now we can do this in the same way. It's just going to be a little bit more complicated because you're going to get fractional coefficients. And this is a very common thing you're going to run into with completing the square. So you need to be comfortable with fractions and doing calculations with fractions. So here you see we get x minus, half of that, the x coefficient we had there. So 8 over 3, half of that is 4 over 3. That's getting squared. And then we subtract the square of that number that we had, which 4 over 3. If we square that, it becomes 16 over 9. So that then cancels out the constant part. So we then just get the x squared in the x term, which is what we started with. So you see, if we expand that out, that will come back to x squared minus 8 over 3x, which is what we want. But once we've now got it into this form, we can now solve it. So if we add 16 over 9 to each side, you'll find you'll get this. We can then square root. Fortunately, we've got 25 over 9, which square root's nice. We can square root nicely into 5 over 3. Now we get an answer of basic, like if we had 4 over 3 to each side, so we basically got 4 over 3 plus or minus 5 over 3, and so you'll then get x equals minus 1 over 3 or positive 9 over 3. So, like I said, yeah, it's essentially the same thing. You've just got to be comfortable with fractions, and if the coefficient of x squared is not 1, you've kind of got to divide through by that number uh, to then make it 1 before you try and complete the square. And, hence why you then, often get fractions. So, yeah, completing the square, often quite a high grade question because you can see it's quite a lot going on there. Finally, the quadratic formula, which is the more straightforward method, we often use when we have like calculators available. You could use this for programming a computer to solve a quadratic. So something like this. So we're looking at the general form of a quadratic here. So you know where we get it to the x squared term, be it x squared term, x term, constant term equals 0. And here we're looking at the general form. So for general coefficients a, b, and c, we can then write the solution like this. And we'll see at the end where this actually comes from. So you see we can write the solution of the quadratic in terms of those coefficients. And this is then important to remember, to be familiar with. Check it, in your exam if you're given this or not. So say if we had an example like this, which might be more complicated, to solve, certainly can't factorize it. We could then plug in those values to the quadratic formula. And you just need to be very wary about how you plug them in. So, and what the coefficients are. So coefficient of A, the A coefficient is going to be 10. The B coefficient is minus 9. So be careful, that minus sign is part of that term. And then C is positive 2. So when you substitute it in, the minus B, that's going to be minus 9, so it becomes positive 9. B squared, just be very wary, you're squaring minus 9, so it's minus 9 times minus 9 becomes positive 81, not negative 81. So be careful of that. So if we simplify that, you basically then just got to use your rules of BIDMAS to calculate this out. Just be very careful. It's easy to lose marks here because there's a big calculation. And you see you're basically going to get 1/20th of 9 plus or minus 1. Because you see 81 minus 80, we get 1. Square root of 1 is plus or minus 1. So we get 10 over 20 or a half. Or we're going to get 8 over 20, which is 2/5. So that's just an example using the quadratic formula. Relatively straightforward. You just got to identify your coefficients properly, plug them into the equation correctly, make sure you do the right order of operations, and you'll work out your x. So we have an important part of the quadratic formula is what's known as the discriminant, which is this part, the b squared minus 4ac, the part inside the brackets. So this is just a small thing, often asked in more advanced problems. And it indicates how many solutions an equation is going to have. Like you see here, if it's greater than 0, we're going to get 2 solutions. If it's equal to 0, we only get 1 unique solution. If it's less than 0, we get no real solutions. So let's take a look at that quickly. Like, why is that the case? Well, think about it. It's that square root. The plus or minus that square root is what produces the 2 solutions. You get plus or minus that square root. Now, think about it. If b squared minus 4ac is positive, the square root of that is just going to be some number. So we do plus or minus that number, we get 2 solutions. If b squared minus 4ac is equal to 0, we are then going to have plus or minus 0. So, which doesn't make a difference, does it? If you add or minus 0. And so you see there, we're going to get 2 solutions that are equal to one another. Hence why we only get 1 unique solution. Finally, if that is less than 0, now we're trying to square root a negative number, which can't be done, not with what are known as real numbers, which are numbers that we work with every day. There's a whole other system of numbers known as complex numbers, which you don't really learn about until at least A level, if not beyond. So you don't have to worry about that. So we say here that there are no real solutions. You do still technically have 2 solutions. They're just part of this, complex number system. So yeah, but at GCSE, you just need to know this basically produces 2, 1, or 0, depending on its discriminant. And you can see why that is. And one typical kind of question you might get on something like this, again, another high grade question, this is given a quadratic equation like this, where you see that constant is unknown. We've got just an unknown plus c, and we're told that this has only one unique solution. Find what the value of c is. Okay, that basically means the discriminant is 0. So what we can do is try and calculate the discriminant. So we know it's going to be b squared minus 4ac, b is 6, a is 1, c is unknown c. Well, we can substitute that in. And because we're told this has only one unique solution, we know that must equal 0. So now you see, we've got a little equation there for c. We can solve that. 4c equals 36, c equals 9. So that's an example of using the discriminant. So if we're told something has only one solution or two solutions, referring to the number of solutions, you should be thinking, discriminant. That's what tells us how many solutions there are. So, okay, right, let's get a move on because I appreciate this lesson's getting on quite long, but there's a lot to do in it. It's a lot of quite advanced stuff. But we've done the bulk of it now. So now we're just looking at some other nonlinear equations. So we've got things like this, like algebraic fractions. We can use much of what we've already know about regular fractions with numbers, and we just need to apply it in an algebraic way. So here, if you add two fractions, we have to make the denominators the same first, and then we can add across the top. So you see, we times the first one, the top and bottom by 3, the second one we times top and bottom by 4, and then we can add, and we'll get 7 over 12. We could do the same thing with this here. It gets a little bit messy. So you see the first fraction, we're timesing the top and bottom by x plus 1. The second one, we times the top and bottom by 2x minus 3. Or what we could do is think of it as just simply multiplying the whole thing through by 2x minus 3 and x plus 1. So you see that first fraction, the multiplying by 2x minus 3 cancels out the denominator. Times the top by x plus 1, we get x plus 1. The second fraction, we're multiplying through by x plus 1, will cancel the denominator. And multiplying by 2x minus 3, we just simply get 4 times 2x minus 3. And on the other side, we've got 1 times by 2x minus 3 and x plus 1 is just going to be 2x minus 3 and x plus 1. So that's the key step with solving an algebraic fraction. We need to essentially multiply out those denominators. Once we've done that, you see what we've got here. It's a lot of stuff we've already seen. So a lot of brackets here. So if we just need to expand out all those brackets, so I do, x plus 1 is just x plus 1. We multiply that 4 through by the 2x and minus 3. On the other side, we've got a double bracket. So we multiply that out in the same way we saw earlier. Now what we want to do is bring all the terms to one side. So if we just subtract everything that's on the left-hand side of the fraction, we'll essentially get this. So we subtract 8x, we subtract x, we subtract 1, we add 12 to both sides, and you'll get this. And so I've swapped the fraction, the equation around now. So we've got our quadratic on the left. And so you see here, because you see all we had was a constant term, x squared term. It's basically a quadratic. So we can see it's going to reduce to something like this. We can now simplify that because you see there's a common factor of 2 there. So we actually don't have to worry about the whole coefficient of x squared not being 1 there, because we can actually cancel it out quite nicely without getting fractions. And then this can actually be factorized quite nicely. So we get this. And so therefore the solutions are going to be 4 and 1. So that's an example of a quadratic. The key step is that first part where we've got to multiply out the denominators. Then it's just a matter of expanding out all the brackets, bringing together all your like terms on one side. You'll get a quadratic typically, and then you just got to solve that quadratic in the usual way. So you see how things are kind of building upon one themselves. Now, say if you had something like this, again, this is quite an advanced problem. You probably it's uncommon to come across, but it's good to be aware of how you would do something like this. Now, this you wouldn't want to solve in the same way we just did a moment ago, where you multiply out the denominator. Because you see here, if I expand all that out, you might want to try that yourself if you want. You see what we do is we get a cubic term, that 2x cubed on the right hand side. That's going to be a problem because we don't know how to solve cubic equations, and generally you don't encounter them much at a GCSE level. So We don't want to do it that way. Instead, what we do is we factorize the numerator and denominator of that fraction, and we need to look for a common factor. This is typically the first thing you'd want to do anyway. And you see here, we do have a common factor of x minus 5. And so that simplifies quite nicely to this. Now multiply out the denominator. So multiply everything by x minus 2. You'll get this. We can expand out our common, the double brackets, collect together all like terms on one side. And again, you get a quadratic. And we can just use the same techniques we've just learned. In this case, you might want to use the completing the square or the quadratic formula, because this is one that can't be factorized, not with integers at least anyway. Right, okay, so last section. So other nonlinear equations we could deal with, which are higher order polynomials, like say a cubic equation, but you'd only ever get simplified cases like this, where say x cubed equals 32, so therefore x is going to be a cube root of 32, which we could simplify to be this if we wanted to. And then technically you get two complex roots, like what I was saying earlier, which is part of this number system, but you don't have to worry about that, because technically whenever you cube root something, you're going to get three roots, in the same way as when you square root something, you get two roots. But we're only ever going to see one of them at GCSE level. You might get something like this, but the key is to notice that they all have a common factor of x, which we could factorize out like this, and then you see what's on the inside is just a quadratic, and we know how to solve that. So we can solve that in the usual way. And then here, you basically got three things multiplying each other to equal 0. We can solve that in very much the same way we do a quadratic. So each one of those three things could be equal to 0. And that produces the solutions x equals 0, x equals minus a half, and x equals minus 5. So you see we get three solutions there for a quadratic in general. If you've got something like this, like a full cubic equation, the only way they could ask you something like this is if they've already given you, they give it to you, partially factorized like this, in which case we can then solve it, by factorizing that quadratic part. And then again, you then can read off your three solutions if it's equal to 0, because it, again, same logic. If three things multiplying each other produce 0, the only way that occurs is if one of the three things is equal to 0. Finally, last thing, exponential equations. So this is something like this, where you got x is the power of in an equation, and the only way you can solve this really at GCSE level is you need to make the bases the same on, but so you have to have, say here we've got 2 to the power x. We need to make 64 2 to the power something as well. To solve these kinds of equations in general, it requires something known as logarithms, which you won't learn about until A level. So if you are considering doing A level for math, yeah, look, you might want to take a look in that at some point, because it can be quite a tricky subject, but we don't have to worry about it at GCSE level. So what we do is we put this like this, say, because 64 is 2 to the power 8. And once we've got something like this, 2 to the x equals 2 to the 8, well, x must be equal to 8 then. And so we can just read off, equate the exponents. Same thing with something like this. 5 to the power x equals 0.04. If you have to solve something like this, that's 0.04. We need to be able to get that into the form of 5 to some power, and then we can compare the powers. Well, notice that 0.04 is 1 over 25. If we use our knowledge of proportions to convert that to a fraction, 1 over 25 is basically 1 over 5 squared, isn't it? Which is 5 to the minus 2. So we're using our indices laws there. And so now we can read off x is minus 2. Similarly, one like this, you could get a scenario. Again, we need to get the bases the same. It's always the same rule. It's just how you go about it is going to be a little bit different. So 9, notice that 9 is basically 3 squared. So this could be written as 3 squared to the power 2x minus 1. And so therefore, those two powers are going to multiply, aren't they? So it's 3 to the power 2 times by 2x minus 1. And that's equal to 3 to the power 1, essentially. Like 3 is just 3 to the 1, isn't it? So we get 2 times 2x minus 1 is equal to 1 this time. And so now that's a little linear equation. We can easily solve that, and we get x equals 3 over 4. Finally, last case. This would be a particularly tricky one, but I have seen it before at higher GCSE math level. Again, we need to get the bases of those two, x terms. So we need to get those bases the same. And so we can do it like this. So first of all, okay, that 4 to the x, Notice that 4 is basically 2 squared. So it's 2 squared to the power x. Now, we could swap those powers around, can't we? It doesn't matter what order we do it in. So it's basically 2x to the power 2. That 2 to the power x plus 3, we've got two power, the power, there's two powers adding there. We know that's essentially the same thing as when we multiply two exponents. So this would be like 2 to the power x times by 2 to the power 3. So 2 to the power 3 is 8. So you see that can simplify to minus 8 times by 2 to the x. And then I've moved the 16 over. So we can't get this into the nice, neat form as the others, where we have 2 to the something equals 2 to the something else. In that case, what we do is we do something known as a substitution. So we've managed to isolate the tricky part, which is the 2 to the x. And then what we could do is we could substitute it for a different variable, because we can't solve this equation here. But say if I let 2 to the x equal to some other variable u. Well, you see now that looks very familiar, doesn't it? We've got u squared minus 8u plus 16. That's a quadratic. We know how to solve that. So we can just solve that in the usual way. We get u equals 4. Now we go back, because u is this made up variable. We're not interested in what u is equal to. We want to know what 2 to the x is equal to. So we know u is equal to 2 to the x, but 4 is also equal to 2 to the power 2. And so therefore from that we can infer that x is equal to 2. So very tricky problem that. But that's something that could be asked. And so that's something you might have to do if you can't, like I was saying, get into two exponents that you can easily relate. And you might want to get familiar with this idea of substitution, certainly if you're going on to A-level maths, because you do a lot more of that substitutions at A-level. So, okay, that's it. I appreciate that was a very long lesson. So, well done for getting through all that. Non-linear equations, it's quite a big topic, very difficult topic at higher level math. There's a lot of things they can ask you, and we've managed to pretty much cover everything there today, and I hope you've managed to follow that pretty well. So let me leave you this. Did you know the quadratic formula is simply completing the square applied to our generalized quadratic equation, which is ax squared plus bx plus c equals 0. Now, I'm not going to go through all that with you. I'm just going to put it up here on the screen with explanations of what's going on at each stage. You might want to pause at the end of this and go through that and have a look. You can prove that to yourself that yes, the quadratic formula is just simply completing the square on that generalized equation. So there you go. You might not have known that, like where that quadratic formula comes from, like, and why does it work. This is the reason why it works. So here's your chance to pause if you want to. If not, here are your takeaways for today on everything we need to make sure we know. Like I said, big lesson. So might have to rewatch some of this. There's a lot going on. The next one won't be as long, I can promise you that. So next time we're looking at formulas, identities, and functions. So these are different types of equations. So far, we've just looked at equations in general. Now we're looking at particular types and what they mean and when we use them, like what their purposes are. So I will see you there in the next lesson for that.